record. So it is 9 July, and what I want to do is pick up where we left off yesterday. Yesterday we inducted, we presented the fundamental law of inductance, and I gave some previews, some context, some background, some explanation of this is what we're going to do with inductors. This is how they work. But I want to start saying, well, what do we do in circuits? How do we math in circuits? Just like when we did capacitors, just like when we did resistors, we're going to be doing series of principles of series and parallel, current and voltage, and some calculus. Some really, I'm introducing you to differential equation. It's one differential equation, same one we've done before. Tomorrow will be another. Oh, direction. And I wanted to spend a little bit of time lensing it. Okay, so let's dive in. What do inductors do? What is an inductor? How does it work? Well, again, what? It does. It stores energy magnetically instead of electrically, and it releases it in a different way than a capacitor. Exactly what you said, Chris. In particular, what's the essence of a capacitor? How does it release its energy? When does it release its energy? It's got charge stored on those plates. And what happens if you try to change the voltage on the capacitor? Voltage doesn't change discontinuously with the capacitor. Remember, we drew all those darn graphs of voltage as a function of time. And one thing you may have noticed is voltage never jumps with those. We apply a changing voltage to a capacitor, and voltage on the capacitor cannot change discontinuously because it takes some time for charges to flow on and off. Déjà vu? Okay, so likewise with an inductor, voltage across an inductor is proportional to the rate of change of current. If you suddenly change the current, the voltage will pop into existence across the inductor. Voltage only exists when you change stuff, when you change current. And as we will discover momentarily, the inductor makes it impossible to change current abruptly, impossible to change current discontinuously. Okay. From a circuit perspective, we're going to ignore the inner workings of magnetic field for a minute. We're going to ignore the Lenz's law, the geometry of the inductor. We're just going to say the inductor has an inductance L, and the induced voltage across the inductor is negative L times the derivative of the current through it. This negative sign I wasn't spending much time on yesterday. The negative sign is the directionality. Let me define that briefly. In the fourth part of today, I want to go back and connect this with Lenz's law and see that this negative is the same negative that we've been dealing with all the time with magnetism. I should also, this is, before we dive in, this is the inductor symbol, and yeah.
So usually asks for like voltage or something. I just kind of a reminder, is voltage a magnitude? Because usually none of the whenever even though there's a negative sign, they usually don't like make it negative.
Sure, it could be negative. What's the voltage difference from the bottom to the top of a resistor? Current's flowing this way. If you look at the voltage here relative to here, that's a negative voltage. Okay. The quick and dirty way to think about this negative, how I think about this, how I interpret this negative, is if current decreases, what's di dt? If current goes down, di dt is negative. Huh? If current is decreasing, the slope of the current is a negative value. the voltage across the inductor is negative, negative, which is positive. The inductor acts like a battery, trying to keep the current going like it was before, reinforcing the current direction. You flip it around, say the rate of change of voltage is positive, current is positive. If current is increasing, then the negative times a positive is a negative. The inductor drops voltage, acts like a resistor, tries to dissipate current, right? Yeah. Okay. So here's our circuit view. We're going to treat this as a magical black box that obeys this equation. Let's set up these equations. So oh God, I can't remember which is the simpler. Let's turn the inductor on. I think this works out to be the simpler differential equation. So what are we going to do? We're going to have a battery with internal voltage. Okay. So I've been writing script E in significant part because for a while we've been having velocities too. And I've been emphasizing that inductors can be a source of energy. The energy stored in the magnetic field can get released and provide a voltage. Remember, that's the difference between script E and V. Now, if I'm going to be talking about this as a circuit element, let me start talking about this as the voltage, really the change in voltage as I go from one side of the inductor to the other. Yeah. Okay. So the script E is the original energy source for the battery. And I'm going to hook this up via a switch that I turn on at time, you guessed it, t equals 0, through a resistance and an inductance. What happens the instant I close the switch? How much current flows? No. What did I say before about the essence of what an inductor does in a circuit? It prevents, that's true, but it prevents instantaneous changes in current. If you didn't have the inductor, you jump from 0 current to script E over R current. With the inductor, it means you can't change that. I'm going to go ahead and tell you guys the punchline. The current is going to asymptotically increase from its continuous before the switch is closed 0 value, asymptotically rise up to a final value equal to the voltage across the resistor. Well, the current through a resistor alone. When things reach equilibrium, here's another powerful principle to think about. When things reach equilibrium, when current isn't changing, what's di dt?
0.
If current isn't changing, the rate of change of current is 0. What's the voltage across the inductor? So an inductor at equilibrium, an inductor with direct current applied, does nothing. It might as well be a wire. That's a principle you can use, can apply. Okay, so here's our punchline. Spoiler alert. Let's derive this, or perhaps integrate this. Okay, so write down the differential equation corresponding to Kirchhoff's voltage law. How much voltage do I get going through that? E. How much voltage changes across the switch? None. The switch closes at time t equals 0. How much voltage changes here? There's the change in voltage across a resistor. Always IR. Down IR, yeah? Baby. Okay. Now, I always have to think carefully about this. The inductor, the drop in voltage, if current is increasing, oh, for God's sake. No, the drop is negative. Crap. I have to think carefully about this, and it's 9:15. I double check myself before I wreck myself. Double check myself before I wreck myself. No. Crap. It also depends on the direction that you define the voltage, but here I'm intrinsically defining the voltage here with respect to here. Okay, no, it's a minus. It's a minus. God, I hope I'm not saying this wrong 2 times in a row. We'll find out if I predict this behavior. I'll say it's correct. If I predict exponential rise, we'll deduce that that can't possibly be it. Exponentially increasing current would break conservation of energy. And I apologize for not thinking through it clearly at first. Let's find out if I'm right. Okay. The way to solve this linear first order inhomogeneous differential equation is as follows. We've done this before with capacitors, and I've given you the solution. But let me walk you through this. Again, like I said before, wait, who's taking DiffyQ? Just a couple of you, right? Oh, several of you. Good. Many of you. This class is not DiffyQ. DiffyQ is not a prereq for this class. So this is, if you haven't done this before, this is a quick and dirty introduction. For the love of God, if you haven't taken this before, you're not supposed to already know how to do this. Ask as stuff goes along. Okay, what I do, how I solve this is I solve for di dt, which, God willing, I'm going to be able to do di dt, isolate di dt, plus, oh, for God's sake, I'm tired. There. Nah. Huh. Okay. So this is the canonical form of the first order inhomogeneous linear differential equation. I hold whatever. The way that DiffyQ works is called guess and check. You may have heard of this technique before. And the guess and check method, the whole idea behind taking a DiffyQ class is twofold. One, to help you guess better, and two, to help you check better. That is to say, if you guess close to be able to find the correct answer. There's a theorem in DiffyQ that says if you guess for a first order differential equation, one with 1 power to the derivative, if you guess a solution with 1 true undetermined constant, you've guessed correctly. Okay. Technique numero uno, with an inhomogeneous differential equation, there are 2 parts to this. Again, I'm dipping into something that you may or may not have. If you have not had this, treat this as a gift from God, professor, to say that the way you solve this is to break this into 2 pieces. First piece is called the homogeneous bit. Homogeneous? I think I always mispronounce that. Homogeneous part, IH equals simplest possible that kills the inhomogeneity, the term without an I in it. And then what is it called? The particular solution? Someone who's had this more recently than, oh my God, 19 years ago. Tell me if my terminology is wrong. Assume there is no. Okay, So what's the simplest darn thing you ever assumed an equation is equal to? What's the simplest form of equation? Well, if I is zero, then we don't. What I'm going to tackle first is the homogeneous part. I'm going to try to find an I that satisfies this equation, that when I plug in that form of I get equality. If I equals zero, di dt equals zero, those die, and I just get zero equals script e over L. No, that doesn't work. What's the second simplest possible solution? Constant. Yeah, one is a constant. I'm going to say in general, a generic constant. So the homogeneous solution, let's say IH equals a constant. I don't know, A. What's di dt? Derivative of a constant, man. Zero, right? Okay. Plug in this proposal into the original equation and tell me A. Where does it go? You do it. So here's the original diffie Q. Plug these into there. What'd you get? What'd you get? R equals A? Ri. What's Ri? I is A. Work with your neighbor and put this in question B. Again, here is your proposal for I. Here's your proposal for di dt. Plug in, solve for capital A. Three, what you smoking? And can I have some? Oh. Are you elite taxor, dude? Do you know about leet speak? Is that still in popular consciousness? Never mind. Well, I put the answer. Which V, Andrew? Be specific. Oh, I mean, yeah, sure, I'll take it. I mean, I hate capital E because capital E is electric field to me. Jake and Ella are typing EMF. I think that's as good as any. Epsilon, Lucian and Chris. No, it's not an epsilon. It's a cursive E. A bigger var epsilon looks like. Whatever. No. I know. I mean, actually, different textbooks might even typeset it as epsilon. Okay, good. I got people telling me script E over R. Yeah, plug in the proposal. Does this work? Yes. However, if my proposed current is just script E over R, that is boring. That says I have reached equilibrium. Incidentally, what did I hint that my equilibrium current is? Equilibrium current. After a long time, what do I reach? Oh, come on, look, what's the asymptotic value of this line? What?
So if we said that A was a replacement for I, and that script E is the voltage, doesn't that just make M one?
Uh-huh. Yeah. Yeah. Remember the other rule of thumb I said, an inductor at equilibrium might as well not be in the circuit. There's no voltage across an inductor at equilibrium. It might as well be an open, I'm sorry, a wire. What is an inductor made of? A wire. Huh? Okay, so this does not satisfy the initial condition of we start at zero voltage, zero current and taper up. if this can be a solution, if we start at script E over R, it'll stay at script E over R current, blah, 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 who cares? But I don't want this solution. So I want to find the particular solution. IP solves the diffie-q ddt IP plus R over L IP equals, well, I've already taken care of the inhomogeneity, script E over L. My proposed solution will be the combination of IP and IH, the inhomogeneous and homogeneous parts, the particular and inhomogeneous parts. So I'm going to go ahead and say that the rest of the solution ignores the inhomogeneity, script E over L. Can anyone tell me the solution to this differential equation? Riddle me this, Batman. The derivative of a function is negative the original function. E to the negative stuff. Okay, so we've got a trial solution. IP equals E to the negative T. What's the derivative? Negative E to the negative T. I plug that in, I get derivative equals negative. Original equals positive E to the negative T. That almost cancels. What about that darn R over L? How could I get that? What if I multiplied the proposal by R over L? What would di dt then be? What would happen if I plugged that in here? What would I get? Uh-oh. You see that? That doesn't equal zero. Negative R over L plus R squared over L squared. You could pull out an E to the negative T. That doesn't kill what we want. How do I get a constant that only appears when I take a derivative? Variable. Variable should I put the variable? If I put it out in front, that doesn't work. This is the proposed, this is the result of plugging it in, and that doesn't work. Do you see that this doesn't cancel? Does everyone see that this doesn't cancel and equal zero necessarily? Andrew. Yeah, totally. Pull out an E to the negative T. E to the negative T times negative R over L plus what? R squared over L squared? I claim that that had better equal zero. Divide by E to the negative T, that's not always zero. No, that doesn't work unless I guess R, oh, whatever. That doesn't work in general. So it can't be R over L E to the negative T. We've got to find a way to pop down a constant only when I take a derivative. What am I describing? Chain. What's the derivative of this function? Yeah. Plug in our proposed trial solution into the master equation. What do you get? Negative R over L e to the negative R over LT plus R over L times e to the negative R over LT. Does that equal zero? Yeah, I've written the same thing twice with the minus sign. When I have a function that satisfies the equation, what that means is if I plug it in, I get zero equals zero at the end of the day. That is guaranteed to be the one and only family of solutions. There's one additional trick I can play. Remember when I threw in a constant R over L and it appeared on both terms? Does throwing another, not the same constant as before? Oh God, I should say B. I don't want you to think it's the same A. Does throwing a constant multiplier in change anything? No. No. The generic solution, the generic solution to this diffie is the combination of these two parts. Slay the inhomogeneity E over R and take care of the derivative E part. I claim I general as a function of T, E over R plus a constant E to the negative R over L T. I claim, I say that this solves or satisfies di dt plus R over L I equals E over R. E over E, oh, E over L. Do this, plug in this, take a derivative, plug in, and convince yourselves that this works. Take a derivative of our proposal, so shove the proposed solution and its derivative into the diffie Q, simplify. Okay, what's the derivative? Take a derivative for me. Okay, what you said is correct. I'm gonna write it in terms that I think of it, taking the derivative of E over R dies, taking the derivative of constant multiple pulled out front, times E to the negative R over L T, derivative of an E is the E times the derivative of the upstairs. I think what you said is every term of this, yeah? Okay, pluggy in that to that, that to that, what you get? The Does it work? Look, there are easy parts and there are hard parts. Distributing a term and simplifying should not be one of the hard parts of this class. I get negative RB on L e to the blah plus RE over LR is E over L plus R over L times B, that's RB on L e to the blah. Look, negative RB on L e to the blah, positive RB on L e to the blah. E over L equals E over L. Bazinga! It works! This is called the generic universal, general, something solution to this diffie Q. What's B? Is it possible that this one equation can solve this unknown? No. What you have to do with a diffie Q is plug in what we say initial conditions. So if I claim that I at t equals 0 had better be continuous, solve for B. This is question Charlie, C, in the Joule form. What is C? B. Question C is find this undetermined constant. Don't use the diffie Q, use the proposed. Not 0, Andrew. Set I to 0 when t equals 0. Solve for B, not 0. Promise. Yeah, I'm insisting continuity. Current starts at 0. Current can't be two different values at the same time. Yeah. But your result for B and C. Plug in IFT. I of 0. Up or down? Yeah. And it's not I of t, Johnny. It's I at time 0. Look at the formula. No, look at the formula. If you plug time equals 0 into I function,
Oh, I mean, it's not like death.
Carlos Drake Daniel, let's see your answers. Show me the way that you are doing this.
Yeah.
Okay, now Johnny and Ed, you've got a function for I. What happens when you evaluate him when t equals 0?
Only
Plug in t to that function. Good, 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 good. Show me your result. Good. Okay, so what's e to the negative 0? Yeah, I'm taking this function and plugging in t equals 0. So this turns into 1. E over r plus b times 1 equals 0. What's b? B must be negative e on r. What? If I want continuity, I had better start at 0. There's a formula for I. I impose my condition.
Wow, I complicated.
Huh?
Yeah. I just did that.
Okay, so now we've got our master equation with the undetermined constant determined by the initial condition. And I usually see this written current as a function of time equals E over R factored out 1 minus E to the negative R on LT. What? The charging RL equation? Maybe charging is the wrong word. It's not building up charge. What's a better way to put this? How did the textbook put this? The textbook doesn't describe this. Maybe turning on is a better phrase. Okay. What happens when time equals 0? We get 1 minus e to the 0, which is 1 minus 1, I equals 0. And you already plugged in this equation to Kirchhoff's law, the original differential equation that we got from applying Kirchhoff. Okay. So this works. We good. This is the solution. Let's take a short detour. And I want to find the energy stored and also the energy burned in the resistor. How do we get energy in circuits? Always. Where does energy come from? What equation do we always have that involves energy and voltage and current and stuff, land? It is me. Wait, no. I don't have an equation for E energy. I mean, the term, yeah, is you, but I have an equation for power. What's power in circuits? VI. Do we have an equation for I in the inductor? How could I get an equation for voltage across the inductor? Where is voltage across the inductor equation? Okay, you've got V, you've got I. Plug in and tell me the total. Oh, no, this requires 2 steps and you guys are sleepy. Let's do it step by step. If here's E, what's V? Negative L times ddt of what's this derivative? No, what's this derivative? E over R pulls out, derivative of 1. Derivative of negative e to the blah t, the negative pulls out. Derivative of e, ja. Yeah. Okay, so there's a negative sign here. There's a negative sign here, and when I take the derivative, there's a negative sign here. Hmm. No, you don't like it, Chris. Tell me why. Okay, you're allowed.
Oh, so you just move the negative sign.
Okay, pluggy, any. What do you get? V times I is power. What's power? Yeah, plug in. Here's I, here's V. Oh, this simplifies. Hold on. R over L, L over R. This boils. Mhm. Mhm. Hey, do you guys remember IV as power? Really? Promise? Okay, get a tattoo. Go to a tattoo parlor, Chris. Tattooed on your face. So you see it in the mirror every time. IV. How about Ohm's law? Do you remember Ohm's law? What is it? Okay. Capacitor equation. Voltage across capacitor. Tattoo two. You get a tattoo too. Yeah. Okay, so what's power? Negative E squared over R. Yeah. I'm pulling out the constants. Yeah, right. This times this. 1 times e to the negative bs times. What happens when I multiply e to the by e to the? Ah, come on. 6th grade. X to the n times x to the n. Sum the what? Sum the exponents. X to the 2n. E to the blah times e to the blah is e to the 2 blah. Power, the rate at which energy enters the inductor. No, actually, hold on. The power formula tells us the rate at which energy leaves the circuit. Is that right? The energy burned in the inductor. And this is negative, so this is negative. This is energy entering the circuit. No, that's BS. Oh, these pesky minus signs. Do you know what differentiates a good? Do you know what the difference between a good theorist and a bad theorist is? A good physics theorist always makes an even number of minus sign errors. How do we get from power to energy land? Ah, come on. The relationship between power and energy, 121. day one. No, not really. Power is, define power. Energy divided by. Okay, get this tattooed. All y'all get this tattooed. Energy per time, or the derivative of energy. What's the total energy if I've got a function? If power changes with respect to time, how do I get total? Yeah, so integrate this sucker. Over what bounds? 0 to infinity. Okay, so I'd say the energy stored in the inductor, total energy, is the integral from 0 to infinity of power with respect to time. Do it. Question, bleh. Where are we? Question D. Do an integral. Oh, y'all slid it in. Hey, remember, you want points? You want participation points? Either give an answer or ask a question, tell me where you get stuck. You don't have to get it right. You don't even have to do it. You just have to tell me where you get. Hey, I'm silly when I say tattoo it on your face, but I'm sort of kind of serious. You should make a note if I ask for an equation and then express shock that no one knows it. Put it on your notes as stuff to review. If there's something I'm shocked y'all don't remember, that's a sign you should memorize it. What's a negative power, Carlos? 1 over e to the infinity goes to infinity. What's a 1 over infinity? Yeah, I want to find how much total energy is stored in the
Zero.
E is 0. What? Oh, I was thinking scripting. Oh my God. And e to the infinity is infinity. We don't have any e to the infinities. We have e to the negative blah. E to the negative infinity is 0. Anything to the negative infinity, 1 over that thing to the infinity power. What? E to the negative infinity is 1 over e to the infinity. Multiply e by itself infinite number of times to get infinity. Down stats.
Oh, because you have to do final information.
Yeah. Gesundheit. Simpler, Jocelyn and Anne. Simpler. Simpler. Right. Wait. Man. Man. Did I goof somewhere? Did I write something upside down? Did I write something up and down, upside down? E square. Wait. Oh, okay. Yeah. What the balls? Uh, uh. Oh, yeah, no, Jocelyn and Anne, I think you're right. We don't usually express it like that. We'll pull out a thing in a minute. What the balls? Isn't this? I think you're missing a two, though. I'm gonna throw away the minus sign. I goofed somewhere, freaking somewhere. I'm sorry. As I said, stay positive. Pew pew. Energy dissipated, stored by the inductor is a positive number. Must have goofed someone. Yeah, I must have goofed somewhere. What the? Oh, no. Oh, hell. Take out the negative on the ground, but blah, blah, blah. Instructor said so. Oh, I know where it went. Remember how earlier I was mentally trying to reason? It opposes the change, so it acts like a battery. The battery is flipped upside down. We'll reason through that in a second. Yeah, but the voltage drop from positive to negative, where the current is going, is flipped. Voltage opposes the increase. We'll get there. Oh, these pesky negatives. Oh, these pincha negatives, as somebody said.
Oh, it's equal. So that's a name.
He's just integrating E to the. Lucian and Chris, you're missing an E. Yoslin and Ann, you got an extra R. Check your coefficients, both of you.
So the first one is zero. Yeah. Don't get on that, so now we can't answer.
What power is? No social percentage.
Zero minus one. Negative one. Negative zero minus one. Positive one. Zero minus one. Negative one. Divide by two. Negative a half. One minus a half.
One half.
Huh? Experience, man. Did you get the result?
Yes.
Experience. Practice. Practice makes progress. I've been doing this stuff for 23 years. I hope I'm good at it. Yeah. Drop the negative on the what? Because I goofed somewhere. I mean, think about it. Where's the energy come from? The battery. Where's the energy going? The components. The power equation tells us the rate at which energy is being dissipated, or in this case, stored. It's gotta be a positive rate of dissipation storage. Blah. I must have goofed a minus sign somewhere. Huh? Yeah.
So. Yeah, okay, I only ask because mine got negative. And I wonder if I do it for work.
No, I mean, no, IV is power. But at the end of the day, look, I screwed something up with the minus, as I joked earlier. That's,
But it's definitely positive.
yeah, reason about it. Is energy being created in this? No. And I think I know where I dropped my minus sign to. And I can reason through that with you in a minute.
Does our work have it satisfying your?
Yeah, good. That's where we're going in a second. Okay, what's E over R, by the way? Chris told me earlier, what's E over R? Current. Final state current. Yeah. The current after infinity time. Right? When the inductor goes away, it's just the battery and the resistor. So I'm going to replace E squared over R squared with I squared. There's the energy stored in the inductor. What? What?
I don't know why I'm having so much trouble going like that's the second to last line to the last line. Have you seen that?
What's 0 minus 1? What's negative 1? That first term is 1. What's 0 minus 1? Divided by 2?
Oh, negative one half.
Uh-huh. So the second term is negative 1/2. What's 1 plus negative 1/2? That's where the 2 comes from. Hey, what's the energy in a capacitor? Anyone remember that? The V squared. Half C D squared. Okay. Yeah. Delta V is the voltage across it. Sure. Okay, so notice there's an eerie similarity between inductor energy and capacitor energy. They're related. As a follow-up, we've got the current in the circuit. Could you tell me what is the voltage across the resistor because of this current? If you know the current through a resistor, what's his voltage? Chris told me. Do you know? Yeah, you could find the power dissipated by the resistor. Find the energy dissipated by le resistance. Integrate up IV, where V is the voltage across the resistor. Ready, set, go. I will write this down. Current in the circuit. I don't really have to write IL. You know what? E over R is I final, maybe? And I'm going to define tau for this circuit as the reciprocal of whatever hits T time constant. So here we'll have a slightly less gross equation. I'm going to pull the constants into each other, okay? Yeah, are you guys comfortable with me giving terms to make the equation less? I'm just pulling constants together. Okay, anyway. Where's it go? Tell me the voltage, the energy dissipated by the resistor is the current. R amps up.
So the energy dissipated.
Resistor. Oh, hell, wait, no, shit, crap. Energy dissipated by the resistor is infinity. Is infinite energy dissipated by the resistor. I wanted the, I'm sorry, guys, I'm taking detours here. The energy dissipated by a capacitor resistor combination, the energy stored in the capacitor ends up being equal to the energy in the resistor. We're gonna modify this in a moment, and we're gonna find a discharging inductor puts his energy into the resistor. Don't do this, don't do this. You can write, this is another form of writing the current in a, what did I say, not charging, a turning on RL circuit. Tau is L over R. Don't remember. I assigned the homework a long time ago. This might be a homework question. Think of tau equals RC in the capacitor equation. We had e to the negative t over RC a bunch of times till we defined, all right, tau is the time to reach whenever you have its final value or whatever. So here we've got e to the negative t over L over r, negative RT over L. So I'm saying L over R is the characteristic time to reach 1 over E of its final current in this case. Whenever you have an E to the negative blah over blah T, you can talk about that blah as the, I guess the inverse of that blah is the characteristic time. It is 10. I want to do the discharge, the turning off circuit. We did a little bit of this. We did a little bit of this. Should we take a break? We take a 15-minute break. We'll have time to do the last thing I wanted to hit in lecture, plus a little bit of time to start the review process. Go take 13 minutes. Come back at 25, okay? 5 till the half. Density. I need density. If you're following along on the recording, here's a review time exercise. Give this a shot. Okie dokie. Show me with your hands. Show me the functional form. What's the current look like as a function of time? Go slowly so I can look at everyone. Hold on. Does it parabola? Does it, I guess from your perspective, linear? Does it sinusoid? Show me with your fingers. Sketch it out. No, not right hand rule.
No, not.
I versus T graph. Ah, okay. Okay, tell me what is the initial value of current? Big or low? Or infinity?
B.
B. What is the asymptotic? Ooh, spoiler. Asymptotic current. 0. How do you know it starts at a particular value, not infinity, not 0? Ohm's law. But how come you could use V equals IR just for the resistor? How come you don't need to account for voltage across the capacitor? Well, it makes a difference. What is the initial voltage?
At the initial voltage of the capacitor is 0. So
How do you know?
why?
Tell me why.
There's nothing inhibiting the flow.
What equation guarantees there is no voltage at the start? For the capacitor. The capacitor voltage starts at 0. How do you know what equation promises that? Q over C. Voltage on a capacitor is Q over C. If you don't have no Q, you don't have no V. So all the V is dissipated where? In the resistor. What is the initial current through a resistor? This resistor. V over R. Script E over R, whatever. Okay, asymptotically, how do I know it dies to 0? And I never pick on you. How do you know that final current has got to die?
It's like the resistor.
A resistor what?
So maybe the switch is not on, so.
No. I close the switch at time 0. I always turn it on at time 0. Yes, capacitor is fully charged. What does it mean to be fully charged? What is the current when charge is reached final? Chris? 0. Why? If there were still current, what would be happening to the charge? It would change. Charge is the derivative of current. If current current is the derivative of charge. If charge is not constant, you're building up. If the derivative of current is 0, the derivative of current is 0, how much voltage is in the resistor? If the derivative of charge is 0, if I is 0, how much voltage is across the resistor? What is the voltage across the resistor equation? Voltage across the resistor equation, V equals IR. If I is 0, then voltage across the capacitor is then voltage across the capacitor. If the resistor burns no voltage, how much voltage is left for the capacitor? All of it. So if let me pull this down so I can point. Okay. Here's how I answer dose. Here's how I reasoned about dose. We start out with no charge on the capacitor. I mean, that's the long form problem statement. There's no charge here, there's no voltage here. So all the voltage is here. So a big current flows. How much current? E over R. Asymptotically, if we reach a steady state, then there can be no further change in charge. If we were changing charge, we'd not be in an asymptotic state. So if I taper, if charge reaches a constant, then derivative of charge, current reaches derivative of constant is 0. If there's 0 current, how much voltage is here? 0. How much voltage is left? E. And script E. If there's script E volts across here, then how much current? No. If the script E volts across here and script E volts across here, it's another way to say there's no voltage left for the resistor. Okay, so shape of current is. Hey, how do I know that he starts steep and shallows? What happens to a capacitor when I hook it up to a voltage source? Is it initially easy to pump electrons on or hard? The first few electrons cost no energy, right? If there is initially no charge on the capacitor, there's a big initial onrush of current. What does a big onrush do? It charges up the capacitor. Suddenly, the rapid increase in voltage here means there's a rapid decrease in voltage here. Yeah. If this builds up its voltage, there's less left for here. If there's less voltage across the resistor, what happens to the current through the resistor? V equals IR. If V goes down, I goes down. There's a rapid decrease in voltage for the current. The final step, what I would describe for part 2 would be full credit, is the less current there is through the circuit, the less voltage is across the resistor because V equals IR. The more voltage there is left for the capacitor, the charge is building up. The charge is building up, approaching the battery voltage, the max voltage you could have. The closer this gets to this, the smaller the current is left for that. The smaller the voltage, therefore current is left for that. What'd you all say for part 2? How'd you describe the why? Andrew, how'd you describe the why? This is hard. I won't make fun of you if you. If the current looks like that, what's the voltage look like? And what? What's the relationship between voltage and current in a resistor? Voltage in a resistor equation. R is a constant, if that's I. Yeah, the shape is the same. If this is the shape of the voltage in the resistor, what must the shape of the voltage across the capacitor look like? Show me with your hand. Trace it out. Okay. Okay, so if that's the voltage across the capacitor, what must its charge be doing? Voltage rises steeply and tapers off. What must the charge on the capacitor be doing? Yeah, in what way? Show me the shape of the charge versus time for the capacitor. From which finger? How is charge and voltage related for a capacitor? What equation? Yeah, so if C is a constant and here's V across the capacitor, what's Q across the capacitor gotta look like? Yeah. What's the derivative of this function? Wait, hold on. Voltage across the capacitor, charge across the capacitor. We have reason charge across the capacitor rises asymptotically, tapering off. The charge across the capacitor's derivative is the current in the circuit. What does the derivative of this function look like? What's the initial derivative? Daniel, what's the initial derivative of this function look like? How do you tell the derivative of a function on a graph? What is a derivative? No. Just tell me if you've got a function y versus x, what's the derivative look like? Daniel. And can you help? How do I see a derivative on a graph? What does that look like in elementary school, high school language? Anyone know what I'm fishing for? Slope. Slope. What's this slope? Big or little, Daniel? And slope is initially big and tapers off. The current is initially big and tapers off. Okay. Three equations we used here. V equals IR. V across a capacitor is Q over C. The derivative of charge is current. I guess in Kirchhoff's law, total voltage equals voltage across the capacitor and voltage across the resistor. I haven't made you guys explain all this stuff before. Maybe that's a good thing to review more. There are no essay questions on the final exam, but I think if you can do a chain of logic connecting these things, you're more likely to be able to know what equation to use. If you can follow a chain of, well, this implies this implies this implies this, you'll see the connections between different things. We'll do more of this. Andrew, please. Totes. Total voltage has to add up to battery, right? And the charge on the capacitor starts out nothing. That's usually how the problem statement is. We start with an initial uncharged capacitor. Close the switch, turn it on at time 0. It doesn't have to be, for that matter. You could start with a fully charged capacitor, and then you got a very boring solution. Voltage across the resistor is constant. Voltage across the resistor is 0. Voltage across the capacitor is constant. That would be a valid solution. It's just not what we've ever done. Okay, so you asked me to explain why the voltage across the resistor looks like that. I claimed if the capacitor voltage is starting from 0 and accumulating, because charge accumulates, there's less and less voltage left for the resistor to make the total add up to E. Do another problem. Here. Numerical. Don't have to think about meanings as much. E is uniform and points, I should say vector, points in plus x hat direction. Voltage at x equals 8 meters is -2 kilovolts. And voltage at x equals 2 meters is positive 400 volts. Find E. Can use your equation sheet if you gotta. But this is something that we did a bunch of times. Go get those tattoos, everyone. Fundamental relationships are important. What is E and V? How are they related? Where? What? V at x equals 8. Yeah, sure. Why not? Show me what you got. This will be question, find E, that's question E.
Is that big? Is that a two or a seven?
2. X equals 2 meters. There?
Yeah.
It's 2. I make my sevens with a cross. Mm. Ah, follow up here. No one's got it right so far. State the relationship. Defining equation connecting E and V. Part E, find electric field in this region. Part F, give me the defining equation. What is E in terms of V fundamentally? The always true equation. Jocelyn and Anna, correct. Lucian and Lucian, correct. Now double check what you done just did because you didn't apply it correct.
Everyone was like, what? What did you say? What?
Wait, it's because,
Hmm.
wait, I got V1.
Mhm.
Oh, okay, so I can follow.
No one's got it right.
Was that the number right or no one's got that right?
F is right. Everyone's got F right. But no one's answered E right.
Oh, he's wrong.
E is wrong. Everyone's E is wrong.
He's wrong, he's wrong, he's wrong. Are we missing one? No,
I mean, yeah, but that's
But that's
the
wrong.
the magnitude is wrong too. Double check yourselves and don't overthink this. Like I sometimes say, there are easier parts, these are harder parts. This is not a mathematically sophisticated question. You guys are goofing in something simple. What? Uh-huh, and no one's found the slope correctly. Oh, thanks. Wait. Hold on. I can't divide. Okay, yes, sorry, you're right. I'm goofy. Your units are wrong.
No, but he says.
Did you get it? Yeah, give me units and a direction. E field's a vector and it has units. Yeah, the number's right. I can't arithmetic apparently. CG Jalen, there's only one correct answer. Is what right? For F? Yeah, that's F. There you go. Yeah, it just updated there. Yeah, that's right. Yeah, just working on Jake Ellen. Waiting on. Although to be precise, to be picky, to be physics teacher, most of you didn't give me units or directionality. It is a vector field. Got a direction.
Better?
Wrong. Read the question. Read the question statement again. Oh, your F is wrong, by the way. F is wrong, yeah. F is wrong.
maybe it's just. What's wrong with that? Missing.
No, you're right. I done goofed. To be precise, you should state the units and direction of per E.
Oh, so we have the number
Yeah, although I. Yeah,
in the I have.
yes, correcto. F is still wrong. Your F is still wrong. Still effing up F. Yoselin Ann. There's one problem with F. Can you find it?
Oh, yeah.
There's another problem with F.
Are we good?
Can you find it?
No.
You are so good.
Would have been okay. Is that enough?
400 and what? No, not coulombs, not coulombs, not coulombs. Field newtons per coulomb. Coulombs is charge. Okay, so what is the slope of 8 comma negative 2000 connection to 2 comma 400? 2 meters is 400, 8 meters is negative 2000. Shoop. Well, that's the greatest connecting line I ever did see. Delta V over delta X and negative 400. I can multiply. And then more importante, electric field's constitutive relationship is negative derivative of voltage. So negative negative is positive 400 newtons per coulomb in the positive x-hat direction. I mean, read the problem statement, hint, 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 points in the positive x-hat direction. Okay. Okay. Why is it negative? How can you remember its negative derivative? What does that negative even connect to? How come if voltage has a negative slope, field points that way? Where's a positive charge wanna be? Where does a positive charge want to be? Bottom of a voltage well. Remember, voltage is charge times energy is charge times voltage. So if voltage goes in the negative direction, potential energy is also going down. Which direction is the force of gravity? Which direction is potential energy decreasing with gravity? Coincidence? I think not. The derivative of mgy is mg. Negative mg is the force. Force is always negative gradient of energy, potential energy. Don't forget that minus. Okay. That's some review questions. Now, for something which has been pesking the heck out of me, let's talk about direction. The one direction, not the boy band, the one direction of voltage across an inductor. Why you know? So I'm going to give you a current going this way, leftward, through an inductor, and I will specify di dt is greater than 0. I've got a current flowing leftward, and I'm going to try to increase him. Which way must the induced voltage across the inductor go? Which side of the inductor is at the higher voltage?
This is the Lenz's law. We apply Lenz.
You could, if I told you the sense of the windings. Let's do that. So this comes out and around this way. From my perspective over here, this is counterclockwise? No, clockwise. Yeah, so the current is going leftward. If this looks clockwise, so counterclockwise winding sense over here. Which direction must the reflection field point? Okay, Google form, part uno is, what is that? Part G is voltage higher on right or left? No, don't remember. No memories. Hey, Carlos, take a stab. Andrew, take a stab. Stab this problem. Yes. A2 inducte. Here, stab it, Andrew. Give it a shot. Okay, let's reason through this. Let's reason through this based on lens. Pick a direction, the sense of the windings. And it doesn't matter. It doesn't end up mattering. I'm going to pick clockwise from this perspective. Counterclockwise from this perspective, yeah? Show me the right-hand rule that shows me the direction of the magnetic field due to the applied current. It's damn it. Current going counterclockwise. No. Oh, crap. Current in your fingers for a solenoid, current in your fingers, B field is the result. So let's see, if this perspective looks counterclockwise, I think the counterclockwise, from my perspective, current looks B field applied, original, creating B field is left. Oh, for God's sake, that's right from your perspective. Left from stage left, house right.
I'm completely lost.
So to do this, you got to pick a sense of the windings. It ends up not mattering, but for the sake of uniformity, suppose the coil goes out and around winding this way. If the coil is winding this way, which way is the current going? No. Which way is the current flowing through as I flow? Applied current goes this way. Which direction is the current going? If the wire is winding counterclockwise. So if the wire is coming out like this, and the current is going into this way. Right. Right.
Wait,
No.
do you have a screen?
Oh, for God's sake, you know what? I do. Let's look at this down the end view. That's what I was trying to do a second ago. Okay, so if I look at it from the right, I'm going to draw a perspective drawing. Well, not there. I'm going to draw a perspective drawing. Do you guys know what the symbol means? Here's an eyeball. The eyeball is looking from the right. So from the right perspective, here's not perspective, here's the.
So we have a screen in front of us, maybe I can screen. And then how does it go this way or this way?
Yeah, well, that's what
Yeah. that's-
you don't know about your fingers. Okay, what did I say? The windings look clockwise from this sense, they look counterclockwise from this sense. The current is going in the end. So the current is flowing. Current is flowing. That's the opposite of current. That's the opposite a clock goes from this side. So from this side, make your fingers go counterclockwise. Point away from you with your thumb. Make your, that's the freaking direction. Say,
Pace.
if the current is going counterclockwise from your perspective, the B field is coming towards you. Okay, now orient your hand so that the sense of the freaking line, the current is going like this. Current is going like this. The sense of the winding says the field is right, house right. That's what you, most of you said the first time, yeah? That's the sense of the initial B field inside.
So then, what is the exponent where it says the current goes?
I mean, the current goes leftward through both of them. Here's a sketch, here's the schematic symbol.
So the current starts with this.
The current goes
Current went counter-
from your perspective, yes. You just showed me counterclockwise from your perspective, and that's what it should look like here. Yeah. From this end, I'm looking end on over here. Yeah,
So that. What is that mean with the multi-field?
well, then we're getting to that.
Okay.
First step in lens is to find out which way is the initial flux. So the flux is a rightward flux. Is the flux building up? Or is the flux dying off? Flux doesn't go counterclockwise, flux will go left or right.
That was just.
Piercing those surfaces. Current is building up, that's given. So what is happening to the applied flux? Flux is B dA, A ain't changing. Is B increasing or decreasing? Current is going up. What's the equation for field inside of wire? Solenoid? Mu naught N I. If I is getting bigger, so is B this way. The flux is pointing to the right and increasing. From my perspective, looking end on, it's an outflux. Which direction does lens say an increasing flux? Which direction does lens say the reaction flux is? If applied flux is heading left and getting bigger, what does the reaction try to do? Yeah, the reaction flux opposes the change. So which direction do you have to flow current through this, the reaction current goes which? Yeah, the reaction current goes which way? No, it has to oppose. It has to oppose. Yes, to the right. To the right, everybody to the right. There's the final step. The reaction current opposes the initial, the reaction current. Oh, for God's freaking sake, I want to connect these two things. Everything we've said is logically necessary. You guys got it right. It is to the right side is higher. Oh, for God's sake, no, it's simpler. We don't have to freaking lens it. I'm sorry, guys. I am off today. Current is flowing. If current is flowing leftward, current always flows downhill. The reaction current says which direction is the resulting opposition. The opposition is going to oppose this, but if current is flowing leftward, the right side is higher voltage. The total voltage is higher on the right. The total is from the applied minus the reaction. The reaction is in the opposite direction. If current flows left, that shows you the direction of the total. Remember what I said before, though, what I hinted before, the resistor voltage opposes the change, but he loses. The applied wins. The applied wins, yeah. Because the reaction current can't overwhelm the initial. So Lenz tells us that the reaction opposes this increasing. The initial current, the initial total voltage will be less than the applied, bigger on the right, small on the left. If we just had a wire with no induced voltage, this side would be higher, this side would be lower based on whatever the resistance of the coil drop ends up being, the resistance, the very, 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 very small resistance inside. Current always flows from high to low. When we oppose that change, when we oppose a ramping up higher voltage current increasing to the right, we are opposing that with a reaction of reaction plus minus, but the induced never wins. The induced opposes the change, but it doesn't beat the applied. Well, initially, the initial state, actually, if you try to change it instantaneously, the current can't change. The current will have to stay what it is. So the rate of change has to actually, the rate of change of current, what I gave you here, rate of change increasing, is I'm going to try to increase it. I'm going to apply more voltage to the total circuit or whatever, and that will taper up from zero. The current cannot change instantaneously, so the initial dIdt must be zero. This is hard. Lenz's law is hard, and then we're doing something built on top of Lenz here. Whew. Yeah. But, something you can rely on always and forever, current doesn't flow uphill. Positive charges are attracted to lower voltages. Hell, that's what we just did. That's what we just did, right? If voltage is lower, field pushes in the direction of lower. Field force pushes on that direction of the decreasing voltage. It's just the reaction opposes that change. Okay. That's a homework question, by the way. Merry Christmas. Shoo. Whew. Okay. Directionality of applied and the directionality of the reaction field is what I said is correct. It's just it won't beat the applied field. We have attacked the RL circuit. I would like to do the RL circuit for turning the darn RL off. If you take the battery out, if you short circuit the battery so that the inductor the inductor loses its current. That'll take more than 5 minutes. Crappers. Okay, now just one more result. One more result. This will be faster. This won't be as brainy. Here. B field inside the solenoid. What's the B field inside the solenoid? Okay, good. Mu naught Ni, which I'm going to write as number of turns per total length. Yeah. What is the total energy? Gesundheit. Total energy stored. What did we just discover? Total energy is. Half L I squared. I would like to express, oh, for God's sake, we've got two L's. H. Height of the solenoid. I'm sorry. L in that equation is length, not inductance. Okay. I would like to express total energy in terms of inductance of the coil. How can we do that? Not the current, but the inductance. Solve this sucker for I. What do we get? What's I in terms of this? Total turns, yeah. BH over mu naught and if I if I want to express this really in terms of inductance, what's the inductance for a solenoid? You can look at your notes from yesterday class, end of yesterday class. Phi per current. Right? Did I do that? Is that right?
Yeah.
Remember, you multiply by another factor of n because each turn picks up the applied voltage. Yeah? Yeah?
Yeah,
What the flux?
yeah.
Yeah, let's combinify these equations. No, I don't want it in terms of L. I don't want it in terms of L at all. I don't want it in terms of L. I don't want it in terms of I. I want it in terms of B in geometry. So here's I. Here's L. What do you get for total energy in terms of geometry and field? Yeah? Help me simplify. Mu naught n squared cross section b squared. Do I want to simplify that out? No. B squared h over h mu naught. This is square. Mu naught squared n squared. Do it yourself. Do it yourself. You can't trust me. Obviously, today I'm. N squared on n squared. H on h squared. Mu naught on mu naught squared. I get 1/2 mu naught b squared. What's h times cross-sectional area AC? Volume. Oh, wait, hold on a second. Hold on. So I can express this as energy density. Luke, it is your density. And this turns out to be a general result. Deja vu. Anyone remember when we did this with capacitors? Deja vu? Oh my God, this is similar. Next week, when we talk about light waves, we're gonna see that these connect the total energy density combined together. This formula ends up being super important. We can deduce that light is carries a certain amount of energy. I don't think we'll get that far in a minute.
Like through like only for a solenoid though.
No, this is everything. We deduced it for a solenoid, but actually you apply this to any magnetic field anywhere. Yeah, I write that down. Okay. Well, they're talking about the same thing. How much energy is stored in an E field? How much energy is stored in a B field? And we deduce that they're very similar relationships. We're going to use this. I don't think this is actually on this week's homework, but we're going to use this next week, God willing. We're going to use this next week to deduce something super important about electromagnetic waves. Huh? What?
Yeah, energy density.
Yeah, energy per volume. Look, I got energy equals something times volume, divide both sides.
So no, it's today.
Half epsilon naught E squared is what we did once upon a time for capacities.
Oh,
What do you mean?
Okie dokie. Son las 11:30. It is 11:30. Get out of here. But remember that I love you. No, I just torture you. But that doesn't mean I don't love you. It's just because I'm really twisted. Cat? I'd be a great cat.
yeah, you did great.
Yeah. Yeah.
You'd be good on
Oh, okay. You just think anyone. Yeah, office hours, 1:30 to 2:30. And I won't leave after 7:30. Unless I forget, in which case we'll lose it. But I'll talk to you.
But your Zoom hours are like.
No, it's one, I've moved them both to 1:30 to 2:30. So that I remember as much as anyone else. Oh, these teams are nice. So part of why the sequence is set up this way, and the offense is set up this way, is to. I don't have seen. Oh,
We'll have to see this in upper classes.
Yeah, well,
Mechanical.
yeah, a lot, well, not the electricity stuff, but there's a direct connection between electronic things and
Magnetism.
angular motion, springy motion, mechanics things. You want to design a bridge, you will be encountering the exact same different things with different letters in front of the terms. They're actually, Carlos, hold on, there used to be devices called analog computers,
Okay.
which is where you would build an electronic circuit with analogous values of R, L, and C. And then zap it with different sparks to observe what would happen to my analogous bridge or whatever if wind blew this way, that way, or the other way, if I smacked the bridge with this way, that way, the other way, so.
Yeah,
But-
a different question told us about that. That, yeah, when you got his engineering degree, that's what they did. They just had a whole board of,
Uh-huh.
yeah.
You construct an analogy based on this connection. Look it up, analog computer, Heathkit analog computer, they used to sell these for not too much. Wow, not too much. Or pretty much, much more in today's dollars, but anyway. Yeah, big inflation. Okay. I'll Peter's hands.